Good morning, my name is John Huertas Montes and I'm presenting the evaluation of the generalization capability of MobileNet CNN models for temperature prediction in fiber optic sensor based on synthetic spectrogram. Work done together with Francisco Vélez, Victor Aristizabal and Jorge Herrera Ramirez. In the research group, we work with optical signals. These signals can be measured with fiber spectrogram sensor, also called FSS. From these measurements, we can obtain predictions of disturbances in the fiber, such as temperature, bending, pressure, and vibration. Figure 1 shows a diagram of a fiber optic sensor where a laser provides the signals that travels through the fiber. In the path, there is a sector of the fiber in which the disturbance is made. At the exit of the fiber, there is an objective lens to focus the image to a camera that takes the image as in this figure. That is a real spectrogram. Figure 2 is a synthetic FEM spectrogram. The speckle fiber sensor uses these images to measure the disturbances in the fiber, because depending on those disturbances, the distribution of these spots will change. Taking this into account and using machine learning tools, we can predict the disturbances in the optical fiber. For this work, we only measure temperature. The main objective of this work is to investigate the predictive and generalization of the capabilities of machine learning models for temperature estimation when trained on data from various synthetic spectrogram fiber sensors. To combine multiple synthetic datasets to train various machine learning models. Also to augment those datasets using image transformation to simulate real-world disturbances, and to evaluate the performance metric of model trained with several datasets and with and without data augmentation. This will be the methodology used in the work. First, we start by modeling 3 synthetic datasets with the finite element method. This dataset will be combined in different ways to fit several models. To the simplest model, the one that has one dataset, we will apply some data augmentation test, which will be used to limit the data augmentation to obtain better results. Knowing how to limit the data augmentation, we apply that to the most complex model, the one that has the 3 datasets, and test its predictive capability. In the COMSOL multiphysics software, it is possible to generate synthesized spectrogram using the finite element method integrated with MATLAB. The model simulates an optical field propagation through a multimode optical fiber and concentrating on the sensing zone. Using the FEM model, the wave vector equation is used for each mode of the optical fiber. This equation depends on the electric field and the refractive index of the multimode fiber. Additionally, the refractive index can be recalculated using the equation when the multimode fiber experiences a thermal variation. 3 datasets were synthesized using finite element method. 2 of them, the dataset 1 and dataset 3, with most of the optical parameters are the same, except for the numerical aperture and the index of the core and the cladding. After synthesizing the datasets, they are combined to obtain 4 different models, and this is how they are combined. A MobileNet architecture that is fed by the ImageNet database is used as a basis. This architecture showed satisfactory results despite not being a very robust architecture like the EfficientNet or the BGG16 architecture. The MobileNet network is adapted to be a regression prediction model instead of a classifier. First, the hyperparameters for the model, for the mobile network, are optimized with Optuna, which resulted in 50 epochs, 10 triangle layers, and a learning rate of 1.17 times 10 to the power of -4. Then 2 dense layers are added to the output of the mobile network. After testing the efficacy of the models, data augmentation tests are performed in the hope that this will increase the accuracy of the model. In total, 4 image transformations are applied: rotation, zoom, shift, and noise. An example of each transformation is shown in the figure. Figure A represents the original image. Figure B is the original image rotated. This can be seen with the characteristic X. That is what the image was rotated like 120 degrees. Image C represents the image zoomed. Image D corresponds to the shift to the image of the image, which is noticeable in the Y characteristic. And image E is the image with the noise added. The data augmentation is initially done with the alpha model. First with all the consecutive transformations and then with each transformation individually to identify the one that contributes most to the error. The models trained with the previously mentioned combination of datasets demonstrate satisfactory results, with all four models exhibiting a score value exceeding 0.99. This table represents the calculated matrix for evaluating the performance of the model. We can notice an improvement in the root mean square error of gamma, which is almost the half of the error of alpha. While in the delta model, this increased like 10%. But considering that the delta model has at least 2 times more data than the alpha model, we can say that this is a good result. We present graphically 2 models: the alpha model, which has only 1 dataset, and the delta model, which has 3 datasets. According to the above, the alpha model data is first augmented with all successive transformation and then one at a time. This table shows the metric of this test. Alpha augmented is the alpha model augmented with all the transformations, showing a large error with a root mean square error of 10.15 degrees Celsius. The rest of individual transformation, we can see large error in the augmentation with rotation, which has a root mean square error of 5.14 degrees Celsius. So we attribute the large error of the initial alpha model to this transformation. This is verified with the final alpha model, which include all the transformation except the rotation, and this results in a much smaller error, about 35% of the initial alpha error. This figure shows graphically the most representative model of the table. Since they have the ones that give more information about this test. It is noticeable in the first figure the large error of 10.15 degrees Celsius, since it represents the data augmentation with all the transformation. The next figure represents the alpha model augmented only with the rotation. And the last one is shows the alpha model again, but augmented with all transformations except the rotation. As mentioned before, we proceed to perform the same increase of data in the delta model as in the alpha model, without taking into account the rotation, since, as we could see, this contributed negatively of the model. This table shows the metrics of this test, where a clear improvement of 0.27 degrees Celsius in the root mean square error can be noted. As a conclusion, we could say that the CNN model based on the MobileNet architecture demonstrate a high degree of generalization, achieving a score greater than 0.99 across all models, even when training on combined synthetic datasets with varying optical parameters. The gamma model exhibits the best performance with a mean square error 3 times lower than that of the alpha model, highlighting the benefits of using combined datasets, synthetic dataset. Data augmentation further improve model performance, especially when transformation like zoom and shift are applied. However, rotation introduces significant inaccuracies. These results demonstrate the model's ability to generalize across different fiber optic sensors. making it adaptable to a wider range of conditions without the need for retraining on a specific sensor configurations. Thank you so much.